today, guys, is I get really excited by that. Hopefully you've found a rule or a protractor and things like that. I would not like to do this remotely, but we don't have much choice. The first thing we're going to look at is the proof of 30 degrees or pi on 6. So we're just going to look at in terms of degrees. We're going to get to radians a little bit later on. And basically, let's get into radians first. What is a radian? So if you think about what the word radian is, a radian, it kind of sounds like radius, if you think about it. And it actually, that's what it means. It is the radius, okay? So what is a radian? A radian is another measurement for an angle, okay? So we have this thing called degrees, all right? And what is a degree? A degree is basically you have a whole circle and you split it up into 360 even parts. And 1 degree makes up 1/360th of a full circle. Revolution. So if you think about what a full circle is, so this is kind of like what we would refer to as centimeters, okay? When we're looking at radians, you might want to think of it as like inches, you know what I mean? Like, how do we measure it? It's like a different type of measurement, but it measures the same thing. Like inches and centimeters, measure distance. Degrees measure an angle. Radians also measure an angle. Radians is linked to the radius. So if what a radian is, 1 radian is 1 radius one radian is 1 radius around the circle. Is the angle of 1 radius around the circle. So what do I mean by that? So what I mean by that, guys, is if we look at a circle, let's have a quick look at a circle here. We've got a circle. This is my radius. Let's say we start here. I'm saying 1 radian is 1 radius. So if you took the radius, it would go to about there if you stretched it out. Now, how many radiuses are there around a full circle? Well, if we think about it, the circumference equals 2 pi r, which is approximately equal, pi is about 3.14. So it's about, 6.3 radiuses around the circle. So you're going to have 1, 2, 3, 4, 5, 6.3. So you've got a radius here, 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 and 0.3 radiuses. So 1 radian is measuring the angle, and that's it there. So that is what a radian is. That's 1 radius, and that's an angle. So really, to do a full revolution, it's 2 pi in a full radius. So that's 2 pi to do a full revolution is an angle. So we can say that is, do a full revolution is 2 pi. Therefore, if I only did half of an angle, like 180 degrees, that would be pi. If I did a quarter of an angle, well, that would be pi on 2. If I did a quarter, that would only be 45 degrees, which is pi on 4. And that's where we're sort of going with that. Let's look at the questions. Good. So that's what a radian is. So we're going to look at that. We're going to look at radiuses, and we're going to look at that too. So when I see that pi on 6 is 30 degrees, well, if you think about it, pi is 180 degrees. So you can actually split that up into 6 pieces, okay? Oh, that should be going straight up. Okay, and each, if they split them up evenly, each would be 30 degrees, 3, 6, 9, 12, 15, 18. So pi and 6 is 30 degrees. We will get into this a little bit later on, but don't worry about radiuses too much later at the moment. What we want to do is we want to actually try and find some exact values of trigonomical ratios. We have covered this a little bit before. So the first thing we're going to do on this, so if you guys can get out your rulers, we're going to get some lines, and we're going to put a line on. If you've got a protractor, I want you to measure out 30 degrees from here and 30 degrees from here. Now, if you're not sure what 30 degrees is, I will actually show you where it ends up going, and put it to the edge of the circle. 30 degrees would actually take you to the 0.5 mark, so that would take you there. Normally, I'd get you guys to measure this, and you can actually prove it to me. So you'd do 30 degrees there, and then again, starting from the middle, we're going to do another line out of 30 degrees. And you'll have something looking like that. We're also going to put in a line going straight down to make a triangle. Now, if you guys have drawn a circle, please draw that and draw a line going out here and one down. Now, one thing you'll notice is, let's label in, let me know if I'm going too fast. I'm not going to worry about the radian definition. The radian definition is basically 1 radian is the angle of 1 radius around the circle. So it's 1 radius around the circle. So you've actually got 6.3 of those. Really, you've got 2 pi radiuses of those. So that's what a radian is. It's 1 radius around the circle, and it's the angle between that, where it starts and finishes. Going back to here, what you'll realize is that we can start labeling a few things on here. So we know that this is 60 degrees. We also know that this has a length of 1, because if you go from the outside to the outside, you can see that this has a length of 1. This also has a length of 1. And we can also see that this goes from 0.5 to negative 0.5. So this has a length of 1. If these all have a length of 1, we know that this is an equilateral triangle. Therefore, you could also measure these angles. We know that this is 60 degrees in here too. We also know that this is 60 degrees. Okay. Please use your microphone if you want me to slow down or go over anything. Is anyone not sure? All right, the next section. We're going to halve this triangle. So what we're going to do is we're going to halve it straight through here, okay? As I said, this is all about a proof. So this is about, how we can prove specific angles. So this should be going to there, and this should be going to about there-ish. Okay. So you'll have something like that, and then we should put another line in from there straight down to there. And you'll have something like voila. Now, let's label everything we know on this. We did go through this a little bit before. So, we know that this is 1. We still have an angle here. This angle is what? This angle is 60. Just going to zoom in a little bit. That's 60 degrees. We've halved this. If you've halved this, this would have to now be 30 degrees. And we also measured it 30. And this would be a right angle because we came straight down and gone straight across. Now we have this triangle. This length was 1, if you remember before. If we've halved that, now it has a length of a half, and you can even see it on the axis. It has a length of a half. So we know that this is now a length of a half. Okay. We can use Pythagoras' theorem to calculate what this length is. The area of this is going to be 1. The area of this square is going to be 1/4. The area of this square has to be 3/4. We square root that. It's going to be √3 on 2. So that length is √3 on 2. So now what we're going to do, that's our proof of one of the triangles. So what we can prove from here is we can prove a few things. I'm going to get to that.
Sorry, how did you get √3?
Okay, so do you understand that the area of this is 1? The area of this is 1/4. So the area of this one needs to be 3/4.
Oh yeah, okay, sorry. Yep.
No, you're all right. It's a good question. So I'm just going to run through it because if you asked, you're probably not the only one. So 1/2. This is why I like to think of it like more as squares with you guys, because it does help we're coming here. So the area of this, if that's a half, the area of this is 1/4 because it's a half by a half. This length is 1. So the area of this must be 1, right? The area of this must be 1/4. Therefore, you know that the two areas added together need to equal the bigger one. So something plus 1/4 needs to equal 1. So it's 3/4. What I picture in my head, that's kind of how I remember it. And then I go, well, I need to square root it. So I go, well, √3 on √4 is equal to √3 on 2. Whoops. So I know that that is going to be √3 on 2, that length there, as an exact value. And what we're trying to prove here, guys, is exact values of the unit circle. So there's a few things where we're trying to find exact values from this circle, and that's what we're going to understand. We're going to understand, you know, like why is sine 30 degrees the same as sine 150, which is a half. So if you get into your calculator, and what we're trying to do is we're trying to go, for example, yeah. So if we go, if we do trigonometry, we do sine 30 is a half. Sine 150 is a half. Sine 210 will be negative a half. Sine 330 will be negative a half. And I also know sine 390 will be a half. And I know this because of this unit circle. I also, you know, can keep on going and telling you what those. I also know that sine negative 210 is going to be a half. And I also know that sine negative 330 is going to be a half. And that all comes from understanding here. And that's basically what we're trying to use. So we use this as a teaching tool to help you guys to really try and understand what it is. So what we can do now is we're actually going to draw this triangle just out a little bit bigger. And we're going to do that. Draw. I want to insert a triangle. Shapes. Give me a triangle. I want a right angle triangle. It's just not going to give me one. There it is. Okay, we're going to draw a right angle triangle. I'm going to flip this around. Okay, and we're going to try and draw it roughly 30 degrees, make it roughly similar. And I don't want to fill that. Okay, so we're going to put in everything we know here. So the angle in here is either pi on 6 or 30 degrees. Just accept it's pi on 6 for the moment. We're just going to refer back to this later. The angle up here is going to be pi on 3 for 60 degrees. And we know this is a right angle. And we know this has a length of 1. And we know this has a length of a half. And we also know this has √3 on 2. So, I should have moved that all up. Too late now. What can I tell from this? We've done a triangle, right? We measured it as 30 degrees. We first went with 1, 1, 1. We split that in half. We know that's 1, a half. We use Pythagoras to see that's root on 3. So that means we have a few things. Sine 30 degrees. Where's 30 degrees? 30 degrees is here. Sine is opposite over hypotenuse. A half divided by 1 is just equal to 1. Is just equal to half, sorry. So we know that's a half. Why we use 1 as a unit circle is because the denominator, the hypotenuse, is 1. Because if you think about when we're talking about the hypotenuse, we have sine equals opposite over hypotenuse, and we also have cos, which equals adjacent over hypotenuse. Now, if you've got the hypotenuse as 1, sine just equals your opposite, and cos just equals your adjacent, because anything divided by 1 is just itself. So that's why we use the unit circle, because we can just see what our value is. So if I know that's 1, sine 30 is just a half. I know cos 30 is going to be adjacent over hypotenuse. Root 3 on 2 divided by 1 is just root 3 on 2. If we bring up our calculator and I do cos 30 degrees, it gives you this number, which is actually equal to root 3 on 2. It is the exact value of 30 degrees. It's root 3 on 2, this length, which is approximately 8.7 times the ratio is 8.87 to 1 for the hypotenuse. Now we can also figure out a couple other things from this. This isn't just a 30-degree triangle, it's also 60. So if I say what is cos 60? Well, cos 60 degrees, we've got a reference from 60 degrees, and it's adjacent over hypotenuse. It's a half over 1, and that's why cos 60 is the same thing as, sine 30, because it comes from the same triangle. Oh, that's actually a half over 1. Oh yeah, that's a half over 1 too, because they use different ones. And you'll find that there's this similarity between these when they share the same triangles. So what I mean by that is if you have a right angle triangle, and let's just say it's 40, this is a right angle triangle, this would have to be 50, right? Sine 40, that's opposite over hypotenuse, would be the same thing as cos 50, because cos 50 would be adjacent over hypotenuse, which uses the same thing. So that's why you'll find they're the same. So if I say, hey, cos 50, sine 40, they're coming from exactly the same triangle. You could do it for any of the triangles. I could do it for 10 degrees. If this is 10 degrees, that's 90. That would have to be 80. If you think about it, let's choose this side. Well, that means cos 10, because adjacent over hypotenuse, would be the same as sine 80, opposite over hypotenuse. So here we can then go on with sine 60 degrees is equal to what? 60 degrees sine opposite over hypotenuse. It's the same thing as cos 30 adjacent over hypotenuse. So that is root 3 on 2. So if you do sine 30, sine 60, I should say, this number, which is the same thing as root 3 on 2. Now we're trying to find exact answers. So we're trying to find exact values because there's not a lot of exact values in this. There's only some in some of them. And that's sort of where we're going with that. It doesn't work that way if it's not right angle triangle. We're only dealing with right angle triangles. Really good question. So, yeah. Well, yeah, because it only works for right angle. Well, it does work for non-right angle triangles, but you need to have the same ratio So it does, but because this is fixed, it's 90 in here, that's why you can reference it. So mind you, we only use really SOHCAHTOA for right angle triangles anyway, but we can make a non-right angle triangle into a right angle triangle to find the height, because that's just finding the ratio between them. Yep, exactly, Logan. Yep. So the 10 and 80 degree triangle, it's the same triangle it's coming from. So if we go with this, if we got the 10 degree triangle, let me just draw a better one. Think about if you've got a triangle, right? And if I said, hey, you know, if I've got 10 degrees and I say, hey, cos 10 degrees is equal to sine in what? Well, I know that 10 degrees, well, it has to be a right angle triangle, right? And we're talking about this length. Okay, so it's adjacent over hypotenuse in this case. Now, I know that cos theta equals adjacent over hypotenuse. When you think about it, this one is my adjacent for cos. But when you're talking about sine, this would have to be 80 degrees in here, right? So sine would have to be, if I want to do that over that, because that's what cos is, cos 10 degrees is this over this, well, it has to be, you have to read it from this angle, which is opposite over hypotenuse. Okay, so therefore it would have to be sine 80, and you'd find that those values are the same. And the reason for that is because it's reading the same ratio. Because remember, right angle triangles, even though it's very basic, and that's why I was trying to really go slowly through it with you guys, is it's about the ratio of the side lengths. So it's about how big this is over how long that is. And that's what we're trying to do. And it's reading off the same thing. Cos 10 is reading that length over that length. And sine 80 is exactly the same triangle. It's the ratio of that length over that length. Now, I couldn't say sine 70 because if I said sine 70, that's a different triangle. That's 20 degrees here, and that's 70 degrees here. Like that can't be the same thing as cos 10. But sine 70 would be the same thing as cos 20. Or I could say sine 20, which is opposite over hypotenuse, is the same thing as cos 70. Sorry, cos sine 20, which is opposite over hypotenuse, is the same thing as cos 70, adjacent over hypotenuse, because it comes from the same triangle. I hope that makes sense. So yeah, that's where we're going with one of the proofs. And this is how we get exact values of sine 30, cos 30, and so on. So when we come down to here and we look at sine 30 degrees, what we know from the unit circle and from what we've just proved is we can prove that sine 30 degrees is a half. And we also know that sine 30, if that's a half, cos 60 has to be a half because it comes from the same triangle and what we talked about here just before. We know that, you know, sine 30 degrees, opposite over hypotenuse is a half. It's the same thing as cos 60, a half. We also know that the other one here is going to be root 3 on 2. So cos 30 is going to be root 3 on 2, which will be the same thing as sine 60 because it's reading off the same one. So we're going to go down here. And we're also going to put on root 3 on 2. Now, if you haven't got your table up yet, don't stress yet. We'll get onto this next lesson. If you do have your table, and you've printed it out, you can do that. All right, I'm going to leave it there, guys. Any questions on that? I will stop the recording.